Great. Thank you so much, Susan. I appreciate that. So, quantum computing. I think the question it's a quantum leap? Is it a quantum leap? Um, when you look at the description of it out of Webster, it's an abrupt change, a sudden increase, or a dramatic advance. In scientific concepts, quantum leap is rarely used. It's more of a just as a mechanism that we use to talk about something that might be astonishing. It really was a synonym for quantum jump, and quantum jump was what was described as the abrupt transition, an electron, an atom, a molecule from one energy state to another. So that was, that's where it came from, but quantum jump was the real term. And it's an abrupt change in a quantum system. When we talk about quantum systems are atoms, molecules, the atomic nuclei, and as it changes from one energy level to another. So sometimes the system absorbs energy if there's a transition to a higher energy level. Sometimes it loses energy when it goes into a lower level. And this is not a concept that we made up. It's not of our generation. Niels Bohr, in the Bohr model, where he first put together the model that many of us probably saw in elementary or high school, either in high school physics or high school chemistry, where his model of the atom and the molecule were brought together in 1913. When we look at quantum computing is really becoming a type of computation that's going to address all the collective properties of quantum states. And I'll define these as we go along. We'll talk about superposition, we'll talk about interference and entanglement. We'll look at how that can be used to perform calculations, and we'll look at quantum computers. And this is not going to be a physics tutorial. This is kind of a broad brush of what I found was necessary to know when we started talking to some of our clients about how they're using quantum computing. And within my company, we're a group of software, mechanical, electrical engineers. We work to solve problems in a lot of the offshore arenas for exploration, but there are a number of problems, not just in the oil and gas arena. There are a terrific number of problems in putting together offshore wind farms, in putting together wind farms that we have on land, and putting together solar collection systems, where because of the heavy load of computations, quantum computing is going to be able to help really advance that a lot faster and a lot further than what we can do today. So what I'd like to address in this presentation is, why do we care about quantum computing? How will it really affect your business? What's different about quantum computing versus the ones and zeros we work with today with digital computers? Where's quantum being used today? What's the timeline? And how do you want to include it in your technology roadmap? So let's first talk about, why do we care about quantum computing? I think we care about it because with the quantum computing, we now have the potential to revolutionize computation by solving some of the classically intractable problems that we've got. An example, the traveling salesman problem. We talk about traffic optimization, airline flight and fuel economy simulation. An enormous amount of compute power goes into that today. Financial market modeling. The idea that if in a financial market, if I'm in New York, I want to be as close to the point where the fiber optic cables come onto land, because I want to be able to save those microseconds in order to be able to run my simulation faster in order to what to do, what to buy, what to sell. So that financial modeling, if I can get a faster computer, if I can do it much better, then I'm going to make more money. Weather prediction interpretation. if you're familiar with an organization called NOAA, which is the National Oceanographic and Atmospheric Administration, it's based in Boulder, Colorado. They've got probably the fourth largest collection of compute power in the U.S. for sure, and possibly close to in the world. And they run one model, and that's the upper atmospheric weather model. And when I was at Los Alamos, we did a lot of work with them on supercomputers because we had Crays, they had Crays, the top of the line at the time. And when I talked to them and visited them a number of times, what they basically said was, we have one model that we run. As soon as we get a bigger computer or more storage or whatever we can use, we change 2 or 3 variables and we've already saturated that computer. So this idea of weather prediction and interpretation is pretty important, especially now, especially today when we're in this realm of climate change, where especially when I'm here in Texas, I was in New Mexico yesterday, and New Mexico is now to 100% of the state is in a drought condition. We've got drought conditions in Texas, but we also now have had tornadoes and ice storms and snow where we've almost never had them before, at least not in recorded history. So weather prediction is a very important use of this. Chemical compound simulation. How do I create new materials? Think of new materials that I may want to create, stronger meshes for holding together different types of items that I'm going to be using, things to be used in space and on the International Space Station, things to use in surgery. So there's all kinds of new materials that I can put together. We do a lot of work now, but the problem comes back to the combinatorics. How many billions of things do I have to look at, and how do those expand? Pharmaceuticals, we're creating new pharmaceuticals every day. Cybersecurity. Quantum computing has the promise and the curse of being completely, to have the ability to completely destroy any of your systems that you want to use for your password protection. It would be able to find those passwords and find what the password is within seconds, as opposed to today, something that would take weeks or months to do that. So that's really we have to know both sides of quantum computing for cybersecurity, how to make it more secure, and then how to protect against what's going to be happening with hackers. The idea of encryption and decryption, again, is part of my cybersecurity. When I looked at how do I do encrypt, decrypt, if I can do it instantaneously, that's going to be able to add to encryption everywhere. Artificial intelligence, of course, machine learning, that's going to be part and parcel of how do I analyze things to then feed it into this. And then complex manufacturing, things like electric vehicle batteries, which are incredibly difficult to manufacture. One of the other areas that is also incredibly difficult to manufacture is the quantum computers themselves. And so these are areas where this is why we care about it. So if you're in any of these industries, if you touch any of these industries, you're going to find that quantum computing is going to be part and parcel of what you do over the next 5 to 10 years. So how's it going to affect your business? What's really going to happen within your business? And I think when we looked at it, I looked at the Harvard Business Review, and they're saying, quantum computing is going to enable businesses to really better optimize your investment strategies, of course, improve encryption. The other side is going to make it easier to hack if the bad guys have got one, discover new products, and much more. So when you go through the list of what it impacts, these are going to be some of the things that are going to impact your business. There's going to be high levels of investment, and there's going to be a lot of private sector competition to put together these types of computers. The other side of this is it's very heavily math-based, but you're also going to have algorithms and different algorithms and how you're going to do programming. You're not going to be doing programming in C# and C++. You may be doing those on some outbound computers that then feed into your quantum computer, or on the other side, they may be your quantum computer may be feeding data back out to your other traditional systems. And you're going to have to look at how do I dedicate math and science talent to quantum research. It's going to have to, across the board, look at how it impacts it. McKinsey takes a more focused view. Here's an eye chart, so you may have to get much closer to your screen. But McKinsey focuses really on potential use cases, and I think that's the critical aspect. What you want to do in quantum computing is you want to see if there's any use cases for your industry, whether use case if you're in insurance, if you're in banking, if you're in transportation, retail, wholesale, manufacturing, those types of industries all have use cases. And when I look at the use cases, the greatest short-term benefits are going to be in pharmaceuticals, chemicals, automotive, and finance. And I think the value at stake for these industries, and this is really fairly conservative, is about $300 billion to $700 billion. My estimate is that when quantum computing, when we start seeing use cases being enabled with quantum computers that exist today, you're going to see these the value is going to be in the trillions of dollars. So the industries, you've got global energy. Again, chemicals have a high return area. Pharmaceuticals do, automotive does. And again, automotive, the main area here is as we move into more electric cars, and not so much electric cars, but looking at the ideas behind some of the electric transportation with trucks. And that also includes the ideas of autonomous vehicles. And I think we're going to need to have the quantum computing behind what we're doing within the automotive area, especially with autonomous vehicles. Autonomous vehicles, I think we don't understand today how much compute power it's going to take. And I think we're going to have to use some things like quantum computing to pre-compute a lot of things that have to be done as an autonomous vehicle. And then financial services. I think financial services has always been an early adopter of more compute power. The more compute power I can get, the better in the financial area, because I've got so much data with which to work. That's a real key area. So now let's talk about what's different about quantum computing. And here's where we're going to get into some math. And I want to tell you that yes, there will be a quiz afterwards. You can't use your calculators, but you can use your slide rules if you've got them. And I think the idea of having math behind it is important. You don't have to be a mathematician, but you have to understand mathematics, some advanced mathematical concepts. I'll talk some more about that as we get into the math parts of it. But I think there's one of the areas, again, with mathematics is important, is it's an appreciation of math, not so much that you can do it yourself. I was lucky when I was in middle school in 7th and 8th grade. And I was, for those of you in Pennsylvania or who have watched The Office, I went through middle school and high school in Scranton. And my grade school was one of the ones that was lucky enough to be picked as part of an MIT study project that was going on about teaching calculus at an early age. So it was surprising. I was taking calculus classes in 7th and 8th grade, and at that time it didn't seem that I was too young to be scared by it. So ignorance is bliss. I learned calculus at an early age, and then it was pretty easy going in and going into high school and taking the geometry classes and everything else. So that was pretty important. So I think having an introduction to mathematics is going to be critical. You may not have it. I don't have it in enough depth to do a lot of this work, but I know enough about who to hire to do it. So quantum computers are based on a different model of how the world works. In classical physics, classical mechanics, those of us who've had those original, that Physics 101 course, where you roll the ball down the ramp and you calculate these things, it's more mechanics than physics. But in quantum mechanics, um, objects only occur in a well-defined state once we observe them. And I'll talk more about this as soon as I say after we observe them, and many people who've had some physics, some exposure to physics or quantum physics or any of Einsteinian physics, you'll immediately think of Schrodinger's cat, and we'll talk about that. When we look at, or prior to looking at it, prior to doing our observations, any two object states and how they're related is a matter of probability. So I don't have a 1 or a 0. I've got a range of probabilities now. So that's the first thing we have to get our brains around with quantum and quantum computing. When I record data and store it, I do it in a different way. And what it's called now, instead of ones and zeros, it's a non-binary, not a 1 or 0, qubits. And instead of bits, I've got quantum bits of information. So that, in essence, reflects the multiplicity of the different states in the quantum world. That's why I need different computers. I need a different model for my computers. The multiplicity of states really, it gives me a faster calculation for combinatorics. And we'll talk a little bit more about combinatorics. So even a lot of particle physicists, struggle to understand quantum mechanics. And that's, when I spent 10 years at Los Alamos Labs and worked in, at that time, what we euphemistically called the statistics division. Well, we were the ones who did a lot of the analysis of the testing that went on, a lot of the analysis and the predictability of what would happen during those tests and after those tests. And that really becomes one of combinatorics. Many times it would take writing custom code in 6 months to analyze one test. So and these were fairly smart physicists that I worked with. And this was looking at it today, and Los Alamos today is on the leading edge of understanding quantum computer design. That's one of those things that you can't throw enough traditional computers at it. So the quantum mechanics really does a much better job of explaining the natural world than classical physics. And the reason for that is when I do an observation of the world, and think back to, the world is analog, the computers are digital. Well, in reality, the world's quantum, because I don't know whether that leaf is going to fall. It's not a 1 or a 0. It's a probability spectrum, and that's what I have with the idea of quantum. The idea that in the world of commercial computing, machines and software can do a lot of things that classical computers can, but the one big thing your classical computer, your laptop, your iPhone, your Apple Watch can't do is we can't perform combinatorical calculations very quickly. And by combinatorics, what I'm really looking at is I've got, as I walk through this set of possible solutions to my problem, the solutions start to expand as I look at the first one and test it, but now there's 3 more possibilities, and each of those 3 possibilities have seven states. Each of those 7 states have 2 substates, but each of those 2 substates expand into 25. So I start getting an enormous spread. We do this today when we look at doing timings. I'm doing timing studies. This is one of the things that we do on semiconductor design. If I'm doing a design of a semiconductor, of a new chip, well, now I have to look at, as I put this design in place, how do I lay out the layers? What's the fastest way for it? And I now have a multiple solutions based on the layers in my chip versus positioning on the chip. So these are the type of things that we don't do them completely today. What we try and do is, as engineers, what we say is, I'm going to take this path because I think this is the right path. Even though over here there may be a better solution, I never get to it because I'm going this way. So that's what I can do with quantum. I can do all of them. I don't have to just worry about picking what I think is a good path. Digital computers, and to remember, before digital computers, we had analog computers. And when I think of an analog computer, I think of a big Marchant calculator. And I don't even know if you can find those except in museums anymore, where you've got lots of rows of buttons and you've got this barrel that moves across as you're doing your calculations. That's really an analog machine. It represents your numbers in the machine itself, the actual hardware of the machine. It's way to the digital computers have gotten so inexpensive. We don't even think about the fact of what we can do with Excel when we look at using mathematics on Excel. So this was all brought to us because the digital computers became very inexpensive. Those use a 1 and a 0 and a bit, or 8 bits is a byte. And we can go on and on about the minutia of how to measure that with words and everything else. But the more complicated the code, the more processing power we've got to have. In fact, we end up having to have more processors, and that's how we handle some of those things. But again, there's a lot of tasks that we have to distribute. They have trouble putting them back together. Combinatorics, when I do these calculations, I need to find an arrangement of the items that optimizes some goal, work my path through it, a traveling salesman problem. As the number of items grows, possible arrangements grow exponentially. And when I want to find the best arrangement, digital computers basically have to iterate through every permutation and then the combination of those permutations to find an outcome. And then you identify which does the best at achieving the goal. Many times, it takes longer to do the combinatorics than what the life of the process you're trying to model is. So that's in digital computers, that's what we put up with today. Most times we don't even know that that's what's going on because we're not using that and running out of capacity on our computers with the type of work we do. So in quantum computing, what's different here, and first let's talk about a few definitions. So quantum computing really looks at what I want to do is I want to look at the properties of the quantum states, superposition, interference, and entanglement. And then I use those to do my quantum calculations. So that becomes part of the quantum computer itself. The idea of physically to get an idea of how big is a quantum computer, some of the chips that are 100 qubits and it's measured by qubits as to what you can do are a couple of the ones that I've seen are about the size of 2 decks of cards. That's how big they are. But because of the heat that they generate, there's an enormous amount of plumbing that goes around them, and they usually sit immersed in a liquid nitrogen bath that is the size of a garbage can. So now, the first time I saw one and the first time I started thinking about the processing, it's very disconcerting when you come from a background of, I came out of mainframe computers. When we were using supercomputers at Los Alamos, being on the floor, we had 31, 32 Cray 1 equivalents, but we had some Cray 2s. The Cray 2 was also, its processor was much larger than a couple decks of cards. Its processor was the size of that garbage can, maybe 2 of those garbage cans, but it was immersed in liquid nitrogen because it ran so hot with the computations that it was doing. So, and this would take up, hundreds of square feet, whereas a quantum computer literally could sit on a desktop. if you had a very cold desktop. And so the idea of what's different about quantum computing is just not only getting your brain around the fact of how the compute works, how it works itself to solve a problem, but also the size. And they're going to be really small, but they have to have really cold environments. So we have to think about as that moves along. Quantum state. So in a quantum state, uh, it's a mathematical entity, and what it does is it gives me that probability distribution. So for each possible measurement. So I've got a probability distribution, and I look at all the outcomes. Superposition. So the idea of superposition is much like with the classical waves, the wave theory in classical physics. Any two or more quantum states can be added together. I can superimpose them, and the result will be another quantum state. Now, every quantum state can also be represented by a sum of two or more distinct states. So there's a way I can look at superposition to now I'm adding together. I've got this one state of this one thing that I'm going to observe. I haven't observed it yet. And I've got a second one that may be going in parallel, but they're in different levels and they're in waves as they go along. So the idea then is I can have interference where the wave function, my superposition wave, interferes with itself or adds to itself. And entanglement, finally, it's the phenomenon that occurs when a group of particles are generated. They interact some spatial proximity in some way that the state of each particle can't be described independently of the state of the others. So now I look at entanglement where one particle, when I measure the state of this one particle, it's dependent on the state of these other particles. So I've got multiple ways of looking at it. The way we can use these is if I'm trying to do a calculation, and in the business of oil and gas, we're always looking at seismic data, and seismic data is another one of those areas where once I collect the data, I have an enormous amount of processing. The processing I do is limited, completely limited to how much compute power I've got. Well, I think of entanglement and I think of how do I push a wave through a set of seismic data. And now with entanglement, I can define all the readings I have as that entangled set of data. So think of entanglement as how I process big data. That's the concept that's being presented here. So although it's very physicsy and it's Einsteinian and quantum and everything else, it's very easy for us to map to how we can use these to solve some of today's problems. Schrodinger's equation. So I'll tell you right now, the equation won't be on the quiz. You don't have to memorize it. But it's a linear partial differentiation equation. So those of you who've taken calculus and aced diffie-q, you'll know exactly how these work. I struggled with diffie-q, but eventually got it. And then I had to go into simultaneous, and that was a bigger problem. But this is a differential equations in the mechanical system. And this was a discovery, and think of Schrodinger did this back in the early 20th century. He didn't have a computer to do it. He had pencil and paper and maybe a mechanical calculator, a slide rule. But here's the real difference. At the top, A and B are classical particle wave theory. And at any point in time, I can measure where that particle is. And I know exactly what the state of that particle is, and I know exactly where it is. In quantum mechanics, I've got the rest of these. C, D, E, F, G, H are examples. And I've got my red line and my blue line. And here are two particles. And now as they work over time, they're going to be interacting, they're going to be separating, they're going to be moving, they're going to be, coincident. That's the way the particles are going to be working because it's a probability distribution. I don't know where that particle is until I observe it. And when I observe D, everything stops and I know where the particle is. But while I'm working with, before I observe it, I have this continuum of where this particle, where these two particles can be. And again, with entanglement, I can have as many particles as I want. So again, thinking about this, no more ones and zeros. Where is my qubit? And I don't know where it is until I actually observe it. So interference, there's some of the differences between the classical wave interference and quantum interference. So two different waves interfere classically. In quantum interference, the wave function will sometimes interfere with itself as it's moving through time and moving through space. The idea of classically looking at interference is I add the displacements. In quantum interference, the effect occurs where I've got a probability association with each one on the wavelength. So the absolute value of the waveform is really squared. And the interference involves a lot of the different functions. Classical is a real function. Quantum is a complex function. Again, two distinct definitions in mathematics. Again, I don't want everybody to go out and become a mathematician, but these are just some of the things that you want to understand. If you get into quantum computing and you start looking for a mathematician, you can use this to understand it. Qubits, and the qubits, quantum bits, they're quantum mechanically linked. They're entangled. Went back and talked about entanglement. So once you've got more than one qubit, you've got entanglement. And when you've got two, you can perform 2 squared, 4 calculations simultaneously, 3, 8, and so on. If you've got a quantum computer with 300 qubits, you could perform more calculations in an instant than there are atoms in the visible universe. So that's the power of the powers of 2. So in essence, it's a 1 or a 0, classical computing, versus this. So here are my 2 qubits, and here are the 4 possible states of my 2 qubits. Now, by this time, I know that several of your brains are exploding because you're thinking, I might be able to understand it, but I can't calculate it. There are a lot of different areas that you can look at. And again, this is 3-dimensional. It's not a 2-dimensional problem. It's 3-dimensional. It's linear algebra and conical geometry. When you look through this, you got to say, now, who in the world knows about this? I look at this, and this looks fairly familiar because as an undergraduate, my Bachelor of Science in Engineering was in geodesy, and geodesy is the measurement of the Earth. We're the ones who can tell you that the Earth's not a sphere; it's an oblate spheroid. But the idea that you end up with when you study this is the mathematics you work with are conical projections and conical mathematics, because every object has got its own set of positional information. So I've got my own set in there. So when I look at different objects, I've got to make sure I calculate to one plane. And that's what happens with qubits. So the computing process, when I've got all these qubits in there, I've got to be able to do my calculations, and I've got to be able to match, excuse me, I've got to be able to match where my different particles are anywhere within that sphere. So these are some of the things that when you look at it the first time, you go, my head really is going to explode. But in reality, these are some of the things we use all the time. Qubits have their own coordinate system. So it's essence, I'm looking at my coordinate system for each one of these. Superposition, I've got Schrodinger again. The idea of Schrodinger's cat was a thought experiment that Schrodinger came up with, because when he started looking at quantum physics, he said, I only know I've got a cat in a box, and I can only know whether the cat is alive or dead when I open the box and look at it. Because when the box is closed, it has both states. And that was what he wanted to do that. Amazon is working on quantum computers, and they've cutely enough, called their hardware version lots of Schrodinger's cats. So when I'm not processing qubits, I'm processing Schrodinger's cats. Amazon has a way to do things their own way. Classical computers switch transistors on or off. Quantum computers are going to use qubits, and they're going to be at a certain probability state. That's what's going to happen. When I look at the idea of quantum physics, it becomes fairly surreal to understand that this idea of superposition, they're both going to be 1 and 0 at the same time. In essence, I can do two calculations simultaneously. If I'm really clever and I always entangle two qubits, I can do 4 calculations simultaneously. So this is getting your head around this. That's how the hardware works, and I think we're doing the right thing with quantum computing is we're moving from the hardware to the software to the algorithms. That's going to be the only way we can really make this work. The idea of what are the limits? And again, we're talking about the differences here, the limits on classical computing. It's just ones and zeros. The idea of quantum computing, though, it's not going to replace classical computers because we're going to use those to solve some complex problems, but we're still going to be front-ending them with the ideas of classical computing. Again, big data, we talk about big data. I can't do all the work of big data because I don't have enough ones and zeros. For the most part, I can still only do one thing at a time. As I look at my computer, and it's very fast. If I'm doing teraflops, a billion calculations per. It's actually a billion floating point calculations per second. I've just broken that second up into billionths of a second because I'm doing one thing at each one of those places. Here I'm going to do 4 things or 300 things. It depends on how many qubits I have. And so that's the limit. That's why I need to move forward into using quantum computing. So the idea of quantum computing, I can take qubits and, again, going back to our sphere, back to the circles, I can have a bit at either end of the 2 poles. I can have a qubit anywhere in the sphere itself. And you think of that entire sphere of having, a very high number of positions. Therefore, I can really process an enormous amount of information. And hopefully I'll use less energy doing it because it is smaller. And it's just a different type of design that I'm putting the semiconductor design. And I think they're looking at 1 million times faster, and I think that may be an underestimate. I think we're going to find that they're much, much faster than that. Semiconductor Industry Association, and again, these are still semiconductors. These are still made in fabs. That's the beauty of quantum computing. The manufacturing of it it takes a long time to work everything out, but by 2040, we've already said that we're not going to have the capability to power all the machines around the world. It's just going to expand so much because it's been so inexpensive to really build these machines. So we're going to have, you look at the timeline of where we are in quantum computing, by 2040, we're going to have an enormous number of quantum computers out there, and we'll be using them. You'll be using them. So how's it going to change? Well, it's going to change it a lot because hopefully there'll be applications in just about all industries. As we've automated more, we have had the need for a lot more computing. And I think we'll find some solutions and uses that we really haven't thought of yet. Think back to, as computers came along and we started in the world of personal computers. How many accountants thought they'd have the computer on their desk with a spreadsheet? How many have thought we would be doing our budgeting on that. How many of us thought we'd be watching everything we used to watch on TV or in the movie theaters, that we'd be watching them on our laptops or our iPads or our iPhones. So just as we've been able to change things, and what today for us is mundane was something that was impossible in the 1970s and even in the 1980s, is now something that we just take for granted. We'll see the same thing with quantum computing. Um, when we look at the possibilities, the processing power of qubits, when we perform millions of calculations in an instant, that's going to be a real eye opener, and it's going to be an eye opener in probably every industry. As you think about, even something as mundane, think of the problems we have today with supply chain, and think if we could have one quantum computer that could handle all of Amazon's supply chain. Probably take more than one. They're working on their own. That would be an enormous benefit to them and to us. Um, think about having the ability to schedule airlines much better. Or in the world we're in today, when a weather event comes in, it just is a disaster trying to reschedule things, trying to recalculate what's going on, moving air crews around. These are n-dimensional problems that are almost impossible to solve with a digital computer, but we could solve them with quantum computing. So where's it being used today? I hate to say it, but as a buzzword and jargon, it probably ranks only below AI because of hype. So you want to be careful of the hype. IonQ is a software startup saying they're going to be building quantum software, went public in October at over $2 billion. And it's basically a paper idea. So who's using them? Well, Microsoft Azure Quantum, for all of you who are on Microsoft, the Azure cloud provides things like a development environment, a quantum development environment, quantum scripting languages, Q Sharp. Wonder where Amazon, or wonder rather where Microsoft came up with that. What a clever idea. Put the hashtag on the other side. Quantum computing development is partnering with a company called One Qubit, Honeywell, and several others. IBM, Q Experience, probably the leader right now. I would definitely watch what IBM is doing. They got a quantum network called IBM Q Network 2016. They're forerunners. IBM Q can be accessed on the cloud with a tool called Qiskit. If you Google that, or actually if you just go on YouTube, you can find an enormous amount of information. Amazon's got Bracket, which is another company they acquired, quantum computing with cloud, so they can put together the entire systems as service. They are also setting up a physical lab called the Quantum Solutions Lab, which will eventually have quantum computers in. So Amazon, IBM, and Microsoft are really leveraging their cloud capabilities. And what they're going to be doing is you're going to be doing some calculations on the cloud, feed it to a quantum computer, get your solution back. So that's their model. Google's Quantum Playground, it's got a simulator, user interface, scripting language, 3D state visualization. You want that as you're starting out. Think of your sphere. You've got a sphere around each one of your qubits. And Google announced that it had quantum supremacy for an instant in late 2019. It had a 54-bit processor going, or 54 qubit rather. And then Rigetti Forest is a quantum startup company, raised a total of almost $200 million. They've got a product called Forest that's got a tool suite for quantum computing. And it's got a computing language and development tools and sample algorithms. So this is one of the first ones that in reality, you can get a kickstart on it. This is what Rigetti looks like. And it's basically your laptop feeding into a cloud where it goes through different processors and then creates your output via a quantum computer that's sitting in there. So this is available today. You can try it. You can fly before you buy. In June 25th, 2021, the Fraunhofer Institute, again, major physics institute, um, international reputation. We worked with them when I was at Los Alamos, frighteningly smart people. They've got a quantum system one, their first superconducting quantum computer built by IBM, but they brought it up online. So that's the quantum computer in that stainless steel case. They've got gloves on so they don't leave marks on the case, but also when they move it in and submerge it, it's going to be the first superconducting, meaning down to getting as close to absolute zero as possible. This is the one of Google's quantum computers, and this is the exterior of it where they're trying to link everything together on the outside. This is 2019, Google's quantum computer in Santa Barbara. And then this is the one that I've used throughout my slides. This is IBM's, and this is their largest ever, multiple hundreds of qubits, and this is the one IBM has built. Again, don't let the size fool you. It's about as big as a garbage can. So, what's the timeline for quantum? Well, again, IBM is the one that I think you want to look to for the timeline and further a reality check. We're here in 2022, and there across the bottom are their different machines, and these are chips the size of 2 decks of cards. And today we've got Condor available. Go beyond that, but this is a large number of qubits, 1,000 plus qubits. And they're looking now, it's not until 2023, it's not until next year that I can finally put together my use cases. And their use cases are natural science, finance, optimization, machine learning. And these are, when you look at this developmental roadmap for IBM, timeline rather, you have to think about the realities of what you're going to be doing. And once these use cases are available and implemented, somebody's going to be asking you the question in your industry, can we go to quantum computing? And this is one of those areas that, yes, by next year, I think you will be. And it's an amazing thing to think about because it's going to happen very quickly. And we're going to see an enormous growth in quantum computing over the next year. So, how do you include it in your technology roadmap? I think the idea is what you need to do is you've got to prepare for it, for quantum computing. And I think the first thing you want to do is look at the industry developments, screen the computing use cases. Use cases are going to be important. You don't want to build your own initially. You want to find one that'll give you a roadmap within your own industry. Collaborate with some of the industry entities, join a quantum computing consortium like the QEDC. Understand the risks and disruptions in your company and industries. You have to look ahead and see what problem is it going to solve and how do I reduce the risks? Because there are going to be more risks and disruptions. Think about what happened during COVID. Are you going to partner with or invest in some quantum computing players? Because you want to be able to facilitate the access to knowledge and talent within your company's use case. Consider recruiting in-house quantum computing talent based on your business plan and a positive ROI. Again, I'm just an engineer with an MBA. And I think that anytime I look at this, I really want to look at the risks first. And then if I can navigate the risks, then I want to look at the ROI. What's the return going to be? And if I can get a positive ROI and a manageable, not low, but a manageable risk level, then you want to look at it. And look at it prepare it by building some digital infrastructure that will be able to then interact with a quantum computer. You may not want to buy your own quantum computer. I think a quantum computer is much like an accelerator. What we found with accelerators is it usually took 20 PhD physicists to be able to maintain it and tune it. And I think we're going to find the first that's going to be the same way it's going to be with quantum computing with its introduction. So grow your own quantum capabilities. If you want to do it yourself and get in on this, I think the first thing you want to do is make sure you understand linear algebra, vectors, spaces, matrix transformations, alternative coordinate systems. Remember, here's one qubit, and you're going to have lots of qubits. Download a Q development kit like Qiskit. I think Qiskit, when you download it, it's free, and I think it even comes with you can set up an account on IBM's cloud and start interacting with some of what's on the cloud. Today, you're not going to be running on a quantum machine, but you will be running with some of the cloud algorithms. Learn Python. That's probably the closest language that's being used in some of these. Take some basic quantum computing courses, usually directed by your development kit. If you get on, if you look for Qiskit and training on YouTube, you'll have 100 to look at. I think you want to understand IBM's quantum cloud or the Azure quantum or both. Figure out you want to go with it, look at the IBM cloud or look at the Amazon cloud. Design a use case for commuting within your company and then execute it. And then I think, your technology roadmap, I don't know. I don't know what your roadmap is going to be, but I think you need to figure out how to put quantum computing on it. I think that's going to be critical. So, in summary, why do you care? Well, you've got to define the problem you want to solve. And I think that quantum computing in your industry is going to help solve some problems. How will it affect your business? I think you want to estimate the ROI on quantum within your own business and then move forward based on that. What's different? You want to understand quantum computing. You may not have to do the physics or the mathematics, but you want to understand some of the basics that I presented here. Where's it being used today? I think you want to discover where it's being used in your industry and look at your industry specifically. Timeline, I think you've got time to do this right, but you're going to see more quantum computers within the next 12 months. And then how do you include quantum in your technology roadmap? And you want to update your technology roadmap if you've got one. If you don't have one, you may want to put one together so that you can add quantum to it. Because again, quantum's going to be here next year. So it's a quantum leap. It's an abrupt change. And I think you're going to find that it's a leap that we can all survive.
Don, I want to thank you so much for joining us today.
Thank you, Susan, and thanks to all the participants. And I hope I didn't make any of you faint or pass out with too much mathematics. Cheers.